Good afternoon, students, or good evening rather. Let's begin today's session. So we have been discussing about hydrostatics till the last lecture. We saw the application of Archimedes principle and pressure gradient concept in various different situations. So we'll see a few questions and applications based on those concepts further today. And with that, we'll wind up this section of hydrostatics. So let's begin. So any doubts from H.C. Verma so far? There are a few slightly tricky type of questions in H.C. Verma. If you tried them out, if you have any doubts, please let me know. Okay, so we'll do some questions and discussions in hydrostatics before we continue into hydrodynamics today. So this is a question from H.C. Verma. I think it's question number 25 from the fluid mechanics chapter. Start with this. So I'll just explain the question, what's happening in it first, try it out. So we have a cylindrical container, open cylindrical container, which is completely empty to begin with. Okay. So this cylinder's diameter is given to us as 6 centimeters. Right. So 6 centimeter diameter for the cylinder. And then what we are doing is we are placing an ice cube, a perfectly cubical shaped block of ice of 4 centimeters edge length. So we're placing that in the container. So the side view is like this, that initially you have at the bottom of your container an ice cube of dimension or of side length equal to 4 centimeters. Now we have to assume that with passage of time, the ice melts evenly from the 6 surfaces. So the shape of the ice cube always remains cubical. Okay. So initially this is our situation. Now as the ice melts and the shape remains cubical for the ice cube, after some time we have a layer of water. Okay. And the ice cube has become smaller in dimension. This is the situation initially. Now we have to find the size of the ice cube. Let's say it is L into L into L, where L will become less than 4 centimeters. At the instant when it loses contact with the bottom surface. Okay, so in other words, the layer of water that is formed on the side of the ice, it starts to apply enough buoyancy on it so that the ice will start to float. So find the instant when or rather find the size of the ice cube at the instant when it loses contact with the floor of the container. And use the standard values that density of water is 1 gram per cc, whereas density of ice is 0.9 gram per cc. The diameter of the cylindrical vessel is 6 centimeters, and the initial dimension of the cube, the initial dimension is 4 centimeters by 4 centimeters by 4 centimeters. Assume that the cube melts uniformly from all the 6 faces. Okay, so it remains cubical in shape. Okay, Vineet, we'll discuss question number 8 also. Just saw your message. Okay, so at a later instant, if the ice cube has reduced in dimension to this, where L is less than the initial value of L naught, but a water layer of height h is formed. Okay, then so this is at some later time. Okay. And at this point of time, when we look at the free body diagram of the ice cube, on that there will be a combination of these forces: buoyant force mg and normal reaction. Now the condition for normal reaction to become zero, as we know, is that buoyant force should become equal to mg. This is a required condition. Okay. So this required condition will tell us that the submerged volume should become 9/10 of the total volume of the ice. Okay, so density of water into submerged portion into G should become density of ice into total volume into G. So 9/10 of the volume should be submerged. So this will happen. Okay, so when this first happens, just at the moment when it loses contact, okay, at that time the height of the water column only should become 0.9 L. So it just about loses contact. So this is a condition we have to solve for. Okay. So here the idea is that now we understand from here that when H becomes equal to 0.9 L, that is when the normal reaction contact force is lost. Okay. Now what is the relationship of H with L? Let's understand that. So volume of ice melted, that is equal to L naught cube minus L cube. Okay. So mass of ice melted is density of ice into the volume melted. So that is the mass of water that is formed. Is equal to this quantity. Now that is equal to density of water into volume of water formed. Okay, so this term, this should be density of water into volume of water formed, which will be this. Okay, so again, let's understand how this is making sense. So if you look at the top view of the container at this point of time, so the container's radius is R, let's say, and there's the cubical ice block somewhere inside. And the water is around over here. So this area of cross section that the water is occupying, that is equal to pi r square minus L square. That's why the volume of water that I've taken is this into H. So R is equal to 3 centimeters, radius of the cylinder. Okay. So it's a very interesting question in the sense that when you substitute the values here, you will see that you don't after all have to solve a cubic equation. So this is, let's say, our second equation where we are equating the mass of water with the mass of ice melted. And this was we are going to apply this equation in it, which is the equation for this condition for n to become 0. So there's a special relationship between H and L when normal reaction first becomes 0. So when we substitute that value of H in terms of L in this equation, we'll get the L at that instant when the contact is going to be lost. Okay. So actually in this equation, L and H are both instantaneous quantities and they're interdependent, as you can see. So there's a tendency to make a mistake in this question in a couple of places. The first tendency is to equate the volume of ice melted with the volume of water formed, which is wrong because they have different densities, remember. And second is with the expression for the volume of water, this might in a hurry forget that the water is not occupying the entire cross section of pi r square. It's occupying a cross sectional area of pi r square minus L square. And that L is also shrinking as time is increasing. Okay, so you will see that when you substitute the condition of first equation in the second one and also substitute the values of densities, it kind of simplifies the whole solution because that L cube term cancels out. So luckily for us, we don't have to try and solve a cubic equation, which is otherwise a very difficult task in maths because cubic equations, there's no direct formula or direct algorithm to solve it like you have for quadratic equations. Anyhow, so try to complete this question. I'll give you the solution in a moment. And also, if you're finished with this, then you can start going through question number 8. I will explain that also. Oh, question number 8 is that torque based question. Now, we have discussed this type of thing in class. Vineet, in the first or second lecture, we had discussed the torque due to force from hydrostatic pressure on the side wall of a container. Only we have taken a cubical container. Here, Acha, I have understood. You might have difficulty in understanding the dimensions of the cuboidal container. No? Okay, I'll help you out with that. Okay, so anybody got the answer finally for this? Hope you all understood the equations 1 and 2, yes? Yes, very good, Aman, that's correct. Okay. So substitute equation 1 in equation 2, so you get 0.9 into 3 cube minus L cube. We are taking CGS units on both sides, so it's quite fine. Is equal to 1 into, sorry, 4 cube, my mistake. L naught was 4, correct. Yeah, pi r square minus L square into, now I want to make the value of H as 0.9 L. So that's how this thing turns out. Okay, is equal to square. So, okay. So now this is fairly easy to solve for L, and it comes out to be about Yes. So approximately 2.3 or 2.26. You take pi as 3.14. I think you'll get something like this. There is one question in the H.C. Verma set, which is about simple harmonic motion with the block with a spring attached as it is floating in the liquid. So just leave out that question for the moment. I think that is question number 20 or 18. Just let me check and tell you. Sorry, question 23. Okay. So question 23, just leave it out for the moment. It is a simple harmonic motion question. We'll discuss that in the next chapter when we do oscillations. After we finish properties of matter and fluids, and when we discuss this chapter of oscillations, we'll come back to the general concept of oscillation of a floating object when disturbed from equilibrium. It's a harmonic oscillation. We'll discuss about that. Let's come to question number 8. So I think the difficulty that you might have had in question 8 is understanding the geometry, okay, because it's not specified clearly. But if you go through the language a little bit more clearly, I think you'll understand that he says that the side wall is of dimension 1/2. Okay. Find the total force exerted by the water on the vertical side of area 2/1. Okay. So even that he does not explain. Okay, so we have to take this as length into width into height. The 3 into 2 into 1, the way it's written, we have to consider it as length into width into height. So we have to consider the height to be 1 meter. Then you will get the answer the way it is given. Whereas if you consider in some other order, like the height is 3 meters or something, then other than the first part, the total force on the bottom surface, other parts your answers will not agree. Okay. So anyway, so we have water of density rho and length into breadth into height. So in this particular question, though not specified by H.C. Verma, we have to assume that these are the dimensions. Okay. So it's very simple. Now you have to calculate the torque acting on this wall, for example, due to the force due to hydrostatic pressure, and the torque has to be calculated uh, about the bottom edge. So it's the same type of thing that we had done in class. About this axis, you have to consider the torque because of forces acting on the side wall like this. So if we consider a strip of thickness dy at a depth of y, so on that strip there is a force due to hydrostatic pressure of rho gy into b dy, where b is this width here. Okay. So the torque that this force will be producing will become this force into its moment arm, where this will be the moment arm. So that will be h minus y. So the net torque from y equal to 0 to y equal to h. So the net torque will come out to be like this. Rho gb into hy square by 2 minus y cube by 3 from 0 to h. So this is what it will come out to be. So in this now you substitute the density as 1000 kg per meter cube. Substitute g as 10. Substitute this width b as 2 meters and the h as 1 meter. So then I believe you will get the answer. Whereas if you take the dimensions in some other order, you'll get the torque as a different value. Okay. Okay. Next question we will discuss is this one, 15th one. Okay. So there's a bit of like interesting limiting condition involved in the 15th question. So to finish taking this down or going through it, just start with question number 15. Understand the language of the question. I'll explain in a moment. If you haven't done the question yet, try to interpret the language of the question correctly first. Everything is in that only actually. The solution is very simple, but you have to understand the exact meaning of the question. Okay, so the iron sheets are 1 millimeter in thickness. So to find the maximum edge length so that the cube does not sink in water. So assume that the cube edges are so well welded together, so water cannot leak into the cube. So essentially, it's a it's a thin shell of cubical shape, which is watertight, and it's a hollow thin shell, which is watertight, and that's floating in water because you have that optimal kind of size. This kind of situation, the two-dimensional view like this, and now you want it to have a condition that is able to flow. So suppose it floats in water with this portion X submerged. Okay. Also for the cube, the side length is L, but this thickness is D. So the condition for floating is that buoyant force should be equal to mg. So density of water into the volume of the submerged part. Now D we will take as very small compared to L. So we will take the outer volume as LQ. So this will be this will be the submerged volume. This should be equal to the density of metal into 6 times L squared D. So this is a condition that we get finally, that density of water into X is equal to 6 times density of metal into D into G. Okay. So the length of the portion submerged G is cancelled out. So there's this factor into D. Now you can see the condition for floating is that X cannot exceed and just about become equal to L also, but not. So that means so this is a condition on L. So the minimum value of the length is equal to 6 times density of metal divided by density of water into this thickness. Now take that thickness given as 1 millimeter or whatever, and the values of density given, and you got the answer. Okay, so hope this solution is clear to all of you. So you can see that ratios of these densities is 8. So 48 into 1 millimeter. Okay. So that is 4.8 centimeters. That is a minimum length that is allowed if we wanted to float. Okay, so let's move on to some more questions now. So before this quick recap, last time we had seen that if you have a horizontally accelerated tank, then there is a horizontal pressure gradient in it, which acts because of the pseudo force. So we have a horizontal acceleration E0 for a tank of liquid. Then the surface of the liquid in the tank, first of all, becomes inclined like this. And the easiest way to understand this process of inclination is to understand that in this kind of situation, in this non-inertial frame, your effective gravity actually becomes like this. That G prime is like the effective or apparent gravity. Because in a non-inertial frame moving like this, any object will experience a combination of pseudo force and gravitational force, which makes its apparent weight like this. This is like the apparent weight. So you've seen this number of times in mechanics before. Okay. So this G prime becomes square root of A square plus G square, or in this case, and theta becomes tan inverse of A naught by G. So if the effective gravity acts like this, the surface has to be perpendicular to this. Okay. So that is why the inclination of the surface with the horizontal is going to be that same theta, tan inverse A by G. And also, if we take the direction of x-axis as our acceleration's direction, so we have horizontal pressure gradient, the pressure increases in the direction of pseudo force, that's backwards. And because of gravity, of course, we have this. Okay. So these two become the other important equations. Okay. So let's see a simple level question based on this to begin with. So we have a cubical tank. Dimension L by L by L, like this. And when it is stationary, water is filled right up to the surface. Sorry, not right up to the surface, but up to a height like this. Okay. Now, the tank is given a horizontal acceleration such that the water level on one of the faces just about reaches L. So the water level on one of the faces just about reaches the side length of the tank itself. Okay. So we have to find the horizontal acceleration. In terms of G. And also find the maximum hydrostatic pressure. In fact, maximum and minimum hydrostatic pressure at any point inside water in the accelerated tank. Kevin, check your answer again. Have you applied the concept that volume of water is conserved? On one side, the level is going up. On the other side, the level is coming down also, no? Okay. So getting tan theta is 0.2 with that, is it? By my calculation, is coming as 0.4. Let me check again. Acceleration should come out to be 0.4 times g, or tan theta should be coming out as 0.4. Okay, so now when the tank is accelerated, the level of water will be maximum against this surface, which is at the back, of this of the four faces. So that is almost equal to L. So we'll assume that the water level is like this. So if this water level, let's say H1, has just about reached L, and on the other side, the water level H2 has to be such that, now remember, it says that it just about reaches L. So water has not spilled out. So we'll have to assume that the volume of water remains the same. Which is, in the first diagram, it is H into L square. In the second diagram, it should be the area of this surface into L, which is the depth. So that is half of H1 plus H2 into L multiplied by L square. Sorry, multiplied by L. Okay. So we have H1 plus H2 by 2 has to be equal to H. So here, if H1 is equal to L, that means H2 has to be 0.6 L. Okay. And then you can see, if that is the case, then to directly equate this, tan theta is equal to this. Be getting this. This is the second equation we are using. Yes, okay, good. So that's why we have to be a little bit careful. Otherwise, we can also understand it by applying this kind of principle, that if you look at the pressure at this point and this point, taking this as our x-axis and this as our y-axis, you can also get this equation by that method, that pressure at A will be equal to pressure at B plus rho A naught L, because del P by del X is equal to minus rho A naught. And pressure at A should be equal to P naught plus rho G H1. Pressure at B should be equal to P naught plus rho G H2. So now from these equations, you can see that So you can get this directly. That. So there's an alternate way of coming to this result directly. Okay, so in this kind of a situation, remember, unless we are assuming that water has leaked out, okay, we'll have to conserve the volume of water. Okay, now next, very interesting type of question. So again, we have the same situation to begin with. We have water up to a certain level in a stationary tank. But this time we also have let's say a kind of bob made of wood. So we have a wooden bob which is kept stationary inside the water like this by tying it to a thread which is like this. So the shape need not be perfectly spherical, whatever be the case. Okay. So we have a wooden bob of mass, let's say 200 grams, tied by a thread. Okay. And sunk underwater as shown. Okay. Now in this case, the tension in the thread is observed to be is observed to be 2.4 newtons, taking G as 10 meters per second square. Okay, now next what is going to happen is that we are going to give the tank a horizontal acceleration. Now next, the tank starts accelerating horizontally at horizontal acceleration of 7.5 meters per second square. And the bob is now at a new equilibrium position with respect to the tank. Okay. So find the buoyant force on the bob, the tension in the thread, okay, and the inclination of the thread with respect to the vertical. In the accelerated situation. Okay, Vineet, I'll scroll up. Just let people write down the question, the data of the question, and start working on this. I'll scroll up in a moment. So to think very carefully about all the various forces that act on the bob in the non-inertial frame of the tank when it starts accelerating horizontally. Okay, I'm just scrolling up for a moment. We'll come back to the question. Oh, yeah, sorry. Yeah, Suyash, that's correct. Okay. The only thing is you have to also consider that if the tank is accelerated like this, okay, so obviously the water will be like this. So is the bob going to be at a position like this, or is it going to be at a position like this? Is it case one or is it case two? Okay, think about that very carefully, because just as a hint to you, I'll tell you that in the accelerated frame, the pressure gradient has a horizontal component along with a vertical component. So that also means that the buoyant force acting on the bob will have a horizontal component along with a vertical component. Okay. So the total number of forces acting on the part on the bob will increase quite a bit in the non-inertial frame. There'll be pseudo force, there'll be weight, there'll be tension, and there'll be vertical component of buoyant force because of vertical pressure gradient, and there'll be horizontal component of buoyant force because of horizontal pressure gradient. Okay, so just make sure you take that into account. Okay, I'll just start by giving you the answers. So buoyant force on the bob. this should be 5.5 newtons. Okay. Tension in the thread will become 3 newtons. Angle of inclination will be 37 degrees, but like this, not like this. Yes, good, Naman. Aman, you wanted to verify the answer for the second part of the earlier question?
Yes.
Okay. Maximum minimum hydrostatic pressure are at these 2 points, A and B. So the second partner, I can just do it over here. So pressure at E, hydrostatic pressure at A is maximum, and that will be rho G H1. So that will be density of water into 10 into H1 was 1 meter, right? So 10 raised power 4 pascals. And hydrostatic pressure at B will be minimum, which is rho G H2, and H2 was 0.6 L. So 1000 into 10 into 0.6. I'm not sure I'd given the value of L. So if I've not given the value of L, it will be in terms of L. So just multiply this with L. Here I've taken L to be 1 meter. Okay, Aman, this is clear now? Okay. Now let's move on to this. So in this question, what we have to understand is that initially, when the tank is not accelerated, obviously buoyant force dominates over mg. That is why there is tension in the string and the bob doesn't fall to the ground or fall to the floor. So in the second case, when there is acceleration in the tank, buoyant force's horizontal component will dominate over pseudo force, and buoyant force's vertical component will dominate over weight. Okay. So first of all, from the data given in the non-accelerated situation, okay, when it was in the stationary case, tension, buoyant force, and mg. Now we knew mg is 2 newtons, and tension was given to us to be 2.4 newtons. So from that we can see that buoyant force is equal to 4.4 newtons. So density of water into volume into G is equal to 2.4, whereas density of wood into V into G is 2.0. So we can see that the density of wood is sorry, 4.4. That's what I was thinking this one. So density of wood becomes how much? 2 upon or 20 upon 44. So that is 10 upon 22 or 5 by 11. This is some vital information there. Okay. Or we can just keep in mind these two equations. They are only going to come in handy later. I can solve the whole problem based on this. I need not even calculate the density of wood and all this. Just use this. Okay. So this is the unaccelerated case. Now next, the moment our tank is given the acceleration, the horizontal acceleration. And that to a pretty large horizontal acceleration, 3/4 of g. So we will understand that the liquid inside will take on this kind of a surface. But more importantly, because E naught is 7.5 meters per second square compared to G, which is 10 meters per second square. So now we have a pretty strong horizontal pressure gradient. So we have del P by del X. So if you divide the two equations, you can see del Y by del X, which is tan theta. So that is 3/4. So theta is equal to 37 degrees. Now let's think about the bob and how its free body diagram will look like in this non-inertial frame. So in this non-inertial frame, on the bob's mass, there are a number of forces which are acting. So first of all, let us look at the most basic two ones. There is mg acting vertically downwards, and there is pseudo force acting like this. Because we are in a non-inertial frame, which is accelerated horizontally like this. Then there is the two buoyant force components. So because buoyancy is having, because pressure is having a vertical gradient also. So buoyant force will have a pretty large vertical component, and it will also have similarly a pretty large horizontal pressure component. So these will be this. Okay. So buoyancy's x component will be density of water into the volume into A naught, and buoyancy's y component will be density of water into V into G. Okay. So if you look at these, the resultant of these two will also act along the same line 37 degrees to the vertical as the resultant of the other two forces mg and pseudo force will act like. So this angle you can see will be 37 degrees. Okay. And the resultant of these two will also act along the same angle. Sorry, this is not 37. The angle with the vertical is 37. So this is clear why, because you can see that this tan theta is bx by by, and here also tan theta is a naught by g. So you can see that bx by by is equal to a naught by g equal to 3/4, or tan inverse 37. Okay, so that means the tension will have to act in which direction? The tension will ultimately, you realize, have to act in this sort of direction. Okay, so even if you can't guess that in the beginning, you can assume that tension will have to have a horizontal component which will balance the difference of bx and mg, and it will have to have a vertical component which will have to balance the difference of by and mg. So you realize that the tension will have to be like this. So that's how you realize that if the tension has to be in this sort of direction, so T's x component which will be along the negative x direction actually. So that is density of water minus density of wood into V into A, and T is Y component. So from here you can see that Tx by Ty is also ultimately equal to A naught by G is equal to 3 by 4. So this vector relation is also making you realize this thing, which you can visually understand. So that tells me for sure that my Bob is going to have this kind of a position. It's going to be at a situation where the thread is like this. Such that in fact it's at 90 degrees to this. Okay. So now coming back to this, you can see that the net buoyant force you can say is now earlier we had seen that the buoyant force in that first case was this was 4.4 newtons. Okay, now here G was 10. Now here when you substitute this, let's say that's G prime, that you'll see is 12.5. Okay. So from that you can see that the new value of buoyant force is 5 by 4 times the earlier value of buoyant force. So that's an easy way of doing the calculation. Okay, and then similarly the new value of tension. So earlier I had T naught was equal to the difference of these densities that was 2.4 newtons. Now I have tension is, so that is the difference of these densities into the same factor. Okay. So T upon T naught is again G prime upon G. Three newtons exactly. Okay, so just go through this carefully once and let me know if there's any doubt or difficulty. We'll discuss. So I'll also give you a way by which we can do this analysis a little bit faster. But for that also you have to have clarity about this whole situation first. Then you can see how we can reduce the number of steps in this analysis. Okay, so let's understand a simpler way we can solve this whole situation once you are clear with the whole concept here. So in the non-accelerated case, you can see that buoyant force is density of water into V into G. That is weight of water displaced. So you have that standard equation that we just discussed. Now in the accelerated case, in the non-inertial frame, so remember here in the inertial frame, we had only vertical pressure gradient. Horizontal pressure gradient was 0. Now in this case, we have both vertical and horizontal pressure gradient. So what happens here is that the weight of the object is to be replaced with apparent weight. Okay. This is apparent weight, where G prime is this, and theta is tan inverse A by G. So similarly, the buoyant force has to be also replaced with an equivalent type of buoyant force, which is like this, which is equal to density of water into V into G prime, or this is apparent weight of water displaced. So the moment you do this, you will understand that relationship that we're talking about. So you can see that the tension will now become like this. So the tension will be equal to so if you compare this with this, you can see the difference. Okay. Okay. And you can see that that theta is tan inverse A by G. So your analysis is reduced to this, just three forces, but you understand that your axis along which the forces are acting changes from the vertical axis to the axis along which your apparent gravity acts. So that is the trick of doing this type of question with a faster analysis. Okay, now let's come to one final aspect about hydrostatics, especially hydrostatics in a non-inertial frame. So let us look at a rotating tank, which is also a sort of non-inertial frame. And pressure gradient in a rotating frame. So in a rotating frame, the equivalent of pseudo force is centrifugal force. So let's understand how that affects pressure. So at a very simple level, if we consider something like this, that we have a tube which is kept like this, which is sealed, thin tube, sealed at both ends, filled with water or something. Then the pressure at the two ends of the tube should be equal because they are at the same horizontal level. If we are considering gravity like this, and this is at rest in an inertial frame. But now, if I make this tube start rotating about one of the ends, then the centrifugal force acting on the water starts to create a pressure difference. So if I take this tube now and I keep it on a rotating disc, or I attach it to an axle or something, because of which it is rotating at a constant angular speed omega naught, okay, about this axis. So this thin closed tube filled with water with some ideal fluid of density rho is rotating about the axis shown at uniform omega naught. Okay. So what will happen now is that the liquid will develop what is called a radial pressure gradient. The fluid develops a radial pressure gradient, which we can write as del P by del R, where we can consider this as our radial axis. So to find out this radial pressure gradient, now what we will do is, in this only, we will consider a volume element of fluid of thickness dr at a radial distance r, and we'll make the free body diagram of that volume element in the rotating frame. So we'll understand that the pressure from the left hand side is more than the pressure from the right hand side. So just a moment, I'll tell you. Okay, so when we consider this volume element here, let's say it has a volume of some cross-sectional area into dr, or let's write the area as S. So this is a thin tube of small cross section S and length L. So when you consider the free body diagram of that volume element and consider horizontal forces acting on it. So in the rotating frame, it is at a radial distance of r, or a perpendicular distance r from the axis of rotation. So this is at equilibrium in this rotating frame. So considering only the horizontal forces, in the FBD, Okay, so we will see that there is pseudo force, which is centrifugal force. Okay. Like this, okay. And then there is force due to pressure from either side. So pressure into area, and from this side, P plus dP into area, where P is pressure at R equal to R, P plus dP is the pressure at a radial coordinate of R plus dr. So once again, the change in pressure is the radial pressure gradient del P by del R into dr. Okay. So when you balance these forces in the horizontal dimension for that volume element, you will see that this time there is a pressure which increases with the radial coordinate because the centrifugal force is acting radially outwards. So ultimately what we'll see is that the pressure at the point B at the far end of the tube will be more than the pressure at the point A, which is at the axis of rotation. And that pressure difference will depend on omega square, and it also depend on L. Okay, but we'll see how it depends on L, by what factor it does. Okay, so solving this further, we get very interesting result here. So centrifugal, not pseudo. That this time we get a pressure gradient which is variable. It's like an instantaneous pressure gradient. So del P, so rather and the mass of that volume element will be density into volume. Okay, so that will become density into S into dr. So first of all, the increase in pressure is positive, okay, as we move along that axis, okay, and it's equal to density into omega square r dr. So now substituting this value, so radial pressure gradient multiplied by dr is this quantity. So the radial pressure gradient, unlike the vertical and horizontal pressure gradients in accelerated tanks, the radial pressure gradient is positive and it is variable. It's proportional to r. So that means pressure increases non-linearly with respect to the radial distance. So when we calculate the pressure difference between the 2 points, let's say A and B above, we have to use integration now. We can't just directly say that delta P by delta X is equal to, the uniform gradient. So we have a non-uniform radial pressure gradient. That will tell us that the pressure increases with the radial axis non-linearly. So if I'm used to use this now to find the pressure difference between the points A and B, so what I'll have to do is I'll have to understand that along the radial axis for a distance of dr, the pressure difference created is, so along the radial axis, if I go from A to B, the total pressure difference created is this quantity integrated from R equal to 0 at the point A to R equal to L at the point B. So pressure at B minus pressure at A becomes rho omega naught square R dr integrated from 0 to L. So that's why I was telling you it's a non-uniform pressure gradient, which means it's a non-linear pressure difference. It in fact varies quadratically with respect to distance. Or if I select any two random points on the radial axis, the pressure difference between them will be equal to rho omega naught square by 2 into R2 square minus R1 square. So this is the pressure difference between 2 points at R equal to R2 and R equal to R1 on the radial axis. So in the rotating frame, of course, remember the radial axis is a fixed axis for you. In the ground frame, you will see that radial axis itself rotating at omega. Okay, so for example, if we have a cylindrical tank which is rotating and the liquid inside it is in stable equilibrium, in static equilibrium with respect to that cylindrical tank, then we see a very interesting phenomena that the surface of liquid is a curved surface. In fact, the shape of it is exactly what we call a paraboloid, which is basically a rotated parabola. A parabola is a two-dimensional curve, like y is equal to x square type of parabola. Now, if you rotate that parabola y is equal to x square about the y-axis, then you get a curved surface. You might have heard about paraboloid mirrors and things like that. That kind of thing. Okay. So you get a curved surface, which is called a paraboloid. So if I have this kind of a situation, I have a cylindrical tank which is rotating about its symmetry axis at a constant angular speed omega naught. So rotating cylindrical tank. So the liquid inside it will have this very interesting kind of shape. So had it been stationary, the surface would have been like this. But because it's rotating, okay, the surface is in fact not going to be like this. The surface of the liquid will be like this, not hemispherical, but paraboloidal, this kind of a shape. So inside this tank, if you take this as your radial axis and this as your vertical axis, you will see that you have vertical pressure gradient of minus rho g as usual because of gravity, but you have radial pressure gradient of this much, that non-uniform value. Okay. So that is why now, for example, if you consider this point A, this point B, or some point C on the surface like this, and some point D over here. So if you consider this vertical displacement between C and D as y, and the horizontal displacement between A and D as r, so you'll see that pressure at the point A is equal to pressure at the point C is equal to pressure at the point D, which is atmospheric pressure. Okay. But considering the radial pressure gradient, the pressure at the point the pressure at the point D, which is inside the liquid. So D is this point here inside the liquid. So pressure at the point D will become pressure at the point C plus rho omega square r square by T. And considering the vertical pressure gradient, the pressure at the point D can also be compared to the pressure at C above it. So this will be rho gy. In fact, we are considering the pressure difference between A and D first. Okay. So this basically comes by this thing, PC minus PA is rho omega square r dr integrated from 0 to r. And this just comes from the fact that, again, I made a mistake, it's PD minus PA. Like that. So anyhow, so using this, we get these two relations. So from the two relations, using the fact that these pressures are the same, so equation 1 and equation 2 can be solved to show that Okay, so we have this relation that y is equal to omega naught square by 2g into r square. So the shape of the surface of the liquid in the two-dimensional diagram is a parabola. So if this point has a coordinate r comma y compared to this point O, so you can see this is the relation. So y is some constant into r square. So this is a parabola. So the surface is a paraboloid. Which is the surface that you get when you rotate this parabola about the y-axis. When you rotate the whole thing about the y-axis, you get a concave looking surface, concave from above, that kind of surface. So that surface is called a paraboloid, and this is the equation of that paraboloid. So this tells us that the surface is a paraboloid, which is the sort of concave shape surface by rotating the parabola. Y is equal to some constant into r square about the y-axis. So that is the shape of the surface. Okay, so people hope this concept of rotating tank and the paraboloid surface of the liquid in the rotating tank is clear. So with this, we finish all the concepts and the different types of problems in hydrostatics. Next lecture, we will begin with hydrodynamics. We might look at few more questions at the advanced level of hydrostatics also. But basically now we are set to start with the next section of fluid mechanics, which is hydrodynamics. That will be a relatively shorter section, and after that we'll do properties of matter. So that's it for today, people. Wish you all the best. Thanks for attending.
Thank you, sir.
Okay, people, all the best.